Dear friends, today we are going to see the unit number 6. We call as an IO management, input output management, and especially we are going to see the topics inside that chapter is disk scheduling and RAD technology. That's another important topic which having the numerical part related to the disk scheduling as you already have an experience of CPU scheduling. Similarly, this is another one of the scheduling we call as a disk scheduling. So there are three types of scheduler, as you know, the mid-term, short-term, long-term. So this is a category of the long-term scheduler. Means you have to place the process from the hard disk from to the what ready state, and then from the ready queue or ready state, the process will be scheduled into the what execution mode that we call as the short-term scheduler. So we have to see that algorithms, right, with numerical aspect as well as, and then we will finish up with the red technology, and that's another important topic. So how the very first question, how we means how it's look like, means we know the how this look like, means as we know that is the secondary storage, and whatever the discussions we are going to be see about the disk. So that's a circular disk, right? It's similar like CD and DVD. In today technology, we don't use that one. Means we are having the hard disk and pen drive and some external devices where we can store all the data. But so that topic is they have designed with respect to what disk, right? So we are discussing all the algorithm related to it only, right? So let's see the diagram over here. So as you can see, the different discs are there, and there is one spindle over the all the discs are uh, stacked one above, and there is a one arm assembly that we call as a handler. Understand? So that's arm roll is what it's just going to stick on the particular disc, and you can see there is a up and there is a top and bottom. So there are two modes of this header through which it can read. So we call it as multiple disk read and write. So from top you can also read write, and from the downside also you can read and write operation. So there are few basic terminology as you can see. So every there is a multiple platters we call as a platters. So as you can see there are three platters. Similarly there are n number of platters, and we also call as a cylinders, right? So there it's cylindrical shape, and it's a number of platters put it into the what spindle. So every platters having tracks, right? It will start from the very center of the what platters. So that's a sector number, that's a track number 0 1 2 3 4 up to the what the size of. So maybe as example understand there are 200 tracks, right? It will start from the track number 0 to the track number 199. So every track, now in every track they are having small sectors, so another smaller unit. So the big picture is what the platters. So number of platters, maybe the one side or two side read write operation enable. Then every platters having the tracks, and inside the tracks the small part is what the sectors, and that sectors having the what actual informations which we are going to be performed by read write operations, right? I operations which call it, right? And there is a read write head from the up and what downside as well. So that's a basic structure how it's look like. As now you can see the diagram over here, that person that initially the designer of the disk is holding the initial size of the disk, right? And that disk size is vary. So as you can understand how our technology is converted that bigger one to the what very small hard disk. We can store the as much as amount of data into the whatever systems and external devices. So before initially it was very difficult. So again that disk having diameter as well as there's some standard is 1.5 to 5 point something. So that's a diameter of the what disk. So that's depends. So that's a very initial level. So you can see this a 50-year-old disk size, but in today it's not like that. It's very compact. Let's see the structure of the disk. So similar. So as I explain you in the second slide, where we are having platters, every platters having tracks, every tracks having multiple sectors, and that sectors having the what informations which we are going to perform the read and write operations like that, right? So now the another thing which we call as from the disk structure. So similarly in a CPU scheduling, we try to calculate what waiting time, response time, turnaround time. Similarly, so with the disk scheduling as well as, so there are few parameters which will decide the algorithm efficiency, throughput, like that. So we have to calculate the few times, right? So that we call, the first one is the seek time. To understand the seek time is what, I have to place the particular header, read write header to the head to the what particular sectors. So that time. So first, from suppose let's say initially on a zero track, and my data is reside in a fifth track, and inside a fifth track my data is actually in the particular sector. So I have to move my head from that track 0 to track 5, right? So from 0 to track 5, that movement, the time took from that movement is called as what, seek time, to get the what specific track where the data is reside. So we call it the seek time. Another one is what, latency time. So latency time, as you can see, the disk is rotating. So once I will move to the what specific track number, then the track is again divided into the multiple sectors. I have to be put my head into the sector because the sector contains the data. So then my disk will be rotating. So that time we call as a what, rotational or latency, or rotational time, or latency time, to get that sector. And finally, once you get the track after the sectors, so the time take to transfer the data we call as what, transfer time. So that's a basic information structures which we needed for this. So let's see the very simple example over here. So with the same informations, we can solve that examples. That's a different one. Similarly, we can have a number of examples similar like that. As you can see, there are 480 cylinders are there, right? It is a divided into 120 cylinders zones. So if you divide 480 divided by 120, so they are 4. So means understand there are 4 platters. John with the cylinder in different zones containing also one zone 200 second, 240, 280, 320 sectors. So every zone having a what different sector size. So and assume each sector contains 4096 byte. So you have to calculate the total disk capacity. So understand the question is very simple. You have to just collect all the informations, how many sectors, how many tracks, how many platters, whether it is a dual side or one sided. And once you get all the counting, then you have to just multiply with the what 4096 byte. Then you will get the what actual size of the disk, right? So see how we solve that one. So the total number of sector is what, 120 into 200 plus 120 into 240 plus 120 into 280 plus 280 into 320, because they are 480 cylinder. So means what, 480 divided by 120, so 4 times. So 120 multiplied by 4 and individually is what, 200, 240, 280 and 320. If you sum everything, so we are having total number of sectors. So 124,800 are the what total number of sectors. Now once you calculate the sector, total sectors, then what? I have to just multiply with the what, the size of the one sector. So how much information can store by one sectors? So that is fixed. So 4096 byte. So now if you multiply, so you will get what, 4511180 bytes. You can convert that total byte into the word maybe in GB, MB. If it is asked, okay, represent the total disk size into the GB. So you can convert. So 1 GB is equals to what, 2 raised to 30 bytes, right? Or 1 TB, to raise to 40 bytes. So likewise you can convert into the what the size. So that's a very simple example. Similarly we can go with similar examples where you have to calculate the disk size. So that's a very simple question. So we know the memory, the RAM we talk about when it's required to execute any process. And now we are talking about the disk. So that's a very common difference where the we can represent that question in any different ways. A difference between the secondary storage and primary storage, RAM and ROM, so that you know very well. So volatile, one is non-volatile, the speed, the storage capacity, transfer time. So these all are the parameter you can consider. So I'm not going to be explain this one. So that's you can understood very easily. Now next part move to the word scheduling, which is the important one for this particular chapter. So we are having the different types of scheduling algorithms. If I name, there are 6 different scheduling algorithms. We will see one by one with one examples, and you can apply the same method to any given example, and that will be what will give you the results related to it. So we generally check the performance of the scheduling on the two different time parameter, right? The seek time and rotational latency as we discussed first. The seek time to get the time, the particular track. The rotational latency, the time to take to get the specific sector. So that's what the simple meaning. So we have to minimize the seek time. Similarly, as we have to minimize the waiting time of the process. Similarly, we have to minimize the seek time, so that I can perform IO operations quickly. And seek time is also equal to the seek distance, right? So let's move to the what example. So see, there is a one example given here where it mentioned there is a what 0 to 199. So there are tracks, understand? So how many tracks are there? 200 tracks are there in a dual disk, and we are given the request by the process. So assume there are number of process are there, and every process are looking for the specific track, right? So 98, 183, 37, 120. So that will be what in between, right? So 0 to 199 are the total tracks. So every process are looking for some IO operation for the individual, so for the specific track, and that track can be repeated by the multiple, right? So as you can see here, the different process having different track requests, and the initial situation is what the head, the read write head is pointing what track number 53. So accordingly we will start the what move to the our head to the request. So very first algorithm, which is very basic and very simple one, as we know, the first come first serve. So the request will be in a queue as given. So first request is 98, 183, then 37, like that up to the 67. And initially our read write head is on 53. So you can see here, so that track, as we had seen the diagram of the disk, it's circular, right? Just stretch it into the one single line, so that will be easy for understanding the execution of the algorithm. That's why. So it's 0 to 199, means we are having 200 tracks. So initially head is on 53. So as you can see, the beginning point is 53. Now the next request is what 98. So now my head will move to the what 98. So I have to calculate the what total head movement, right? Or I can say the total seek distance, right? So 98 minus 53, so it's 45. Now the next request is 183. So now my head move to 98 to 183. So again you have to calculate the difference, 183 minus 98. Now next request is 37. So from 183 my head move to the what directly 37. Then 37 to 122, 122 to 14, 14 to 124, then 65, and then 67. So irrespective of a difference, whether the difference is maximum, minimum, that we do not be going to see. The just thing is what we will just check the sequence, and the requests arrive, and then accordingly what we will move our heads. So if you get the difference of all the head movement from the one to another point, and if you sum it, so that total head movement will be what, 640 cylinder, right? The simple. If it is asked the average seek time, so that's the seek distance is again similar to the seek time. So you can divide by the what number of process requested, so that will be the what average seek time, right? So that's a very simple. If I ask what is the any disadvantage of the first come first serve, so yes, you can ask, right? And you can see. So the thing which we discussed in CPU scheduling, with respect to CPU scheduling as well as, so first come first serve having the conway effect. So similarly, that effect is also here. So conway effect is the problem in a first come first serve. So there is no starvation in a first come first serve. It's a simple, easy, have to follow the order in which order the queue is maintained. That's it. Another algorithm, the shortest seek time first, right? So the algorithm is what, just greedy algorithm. Another one you have to be what, check the shortest seek time, right? So accordingly what, we will select the request and we will schedule it. And now again just see it, how we are going to be implement that algorithm. So that will be started from the 53, that is fine. Now out after the 53 you have to be compare, right, the seek time. So the minimum distance from 53 to the any of the given track request, so that's why the 65 is get chosen. And if any other request is there, and if there is an tie between the two process, because the suppose the difference uh, from the 53 is same, then you have to break the tie. So the breaking method is here is what the direction, so in which direction my head is moving. So whether it is moving to the 19 from towards the 199, or maybe the towards the 0. So accordingly you can decide, right? So tie breaking situations will be break by the head directions, head movement direction. Otherwise, if there is no tie, you have to just calculate the difference from the 53 to all the requested track number, and which one is minimum, you have to move accordingly. So after the 65, the minimum is 67. As you can see, the difference is only 3. Then from 63, the next minimum difference is 37, and the next minimum is 14. The next minimum is 98, right? 122 and 124, and then what, 183, and then my algorithm will get stopped. So if you just calculate the difference and sum all the difference, then we will be having 236 cylinder movement, right? So that's the minimum, because that's a greedy approach. As you can see here, it will give you the optimal solution as well as but the bigger problem here with SSTF is what, you have to be having predictions over the minimum difference, and that is totally dynamic situations where you cannot be get that difference initially, right? So for the static problem it's fine, but for the dynamic it is not be applicable. So it will give the minimum movement, but practically it's not possible. You have to it's in dynamic situations, the any track request can be come, right? So that's problematic, but we can combine the two three algorithms and we'll have one actual algorithm. Another algorithm we call as scan, right? So if you read that statement, the disk arm will start at one end of the disk and moves toward the other end, servicing request until it gets to the other end of the disk where the head movement is reserved and servicing the continue. So see that algorithm also we call as an elevator. So as we know that how elevator work, so anybody is requesting from the floor, fourth number floor. So in between somebody is what also push the button at floor number 2, and right now my lift is on ground floor, floor number 0. So understand, it will serve the request for the second floor, then it will reach to the fourth floor automatically. So that's how elevator work, right? Exactly. So Sam, that algorithm works. So see how this algorithm solve the problem. So now for this algorithm, you can notice one thing from the last two algorithms. Our head movement is what towards the 199 from 53 to 199, right? Now suddenly my head is moving towards the what 53 to 0, right? So that another information which we need in questions. Where is my head is right now and moving towards the which direction? So that informations will help you to decide the direction in a scan, right? So in this algorithm that is given, the initial head is what 53 and now my head is moving towards the what 0. So that's why I choose the directions, right? So from 53 you have to serve the request into that directions and reach to the what last trip, right? So as you can see 53 to 37, now calculate the difference. Now from 34 37 37 to 14 and 14 to 0, there is no request for the track number 0, right? Understand, but it will be touched to the beginning point or maybe the last point. So that's why, so that 14 is now you can consider as an overhead. So 14 minus 0 is 14, that is a overhead for us. Then from the 0 it will go to the what next request in the opposite direction. So that's a 65, then 67, then 98, then 122, 124 and 183 and get stopped. So now we just check the calculate the difference and do the sum, and that is the what the algorithm. So the thing that is a practical situations, right, where we will start some work and finish work in the directions and then back to the what another opposite direction and finish the job. So that philosophy work over here and they calculate so that practically is possible, right? So if you calculate the total head moment with this algorithm, it's 20 at cylinders, which is also minimum compared to the what SSTA. So SST were giving 236 cylinder. So that's again depend, right? So how much difference you are having on a different request. So number of movement in a head, IO head, so that will be cause the multiple, that will be cause maximum cost. So now it's performing better, best compared to other algorithm, 208 cylinders only, right? So another algorithms, that circular scan, C stand for circular and they scan. So that's another one. So provide us a more uniform wait time than scan. The head moves from the one end to the disk to the other, servicing requests as it goes. The similar one, but it's a circular fashion. If you see, just move to the diagram directly, how this algorithm solve this scheduling problem. So this is the another one. Again I need directions where my head is moving. So maybe for this example the information will be given that the my disk head is right now on 53 and now it's moving to the what 199, and then calculate total disk movement using C scan. So that's why we choose the directions like that, right? You can read this one. The head moves from one end to reach to the other, servicing request as it goes. When it reaches the other end, however, it immediately returns to the beginning of the disk without servicing any request on the return trip. That's what here. The first 53 go to that directions up to the 199 and serve all the requests in between. So 53 immediately 65, then 67, 98, 122, 124, 183, and there is no request like 199 tray, but that's again overhead 199 to 183. Once it will reach to the what last point 199 tray, then again it will be back right in opposite directions and again touch to the what first point without serving any request in between. So now you can see 199 to 0, it's another big overhead, right? So that 199 minus 0 means 199, that will be added into the what disk head movement, and then again it will be served requests into the what that directions. So 0 to 14 and 14 to 37. So then it will be cost. So treat the cylinders as a circular list that wraps around from the last cylinder to the first one. So that's the structure is different quite here. So that's why it's moving from one to last and last to one, and then again go in that direction. So direction is fixed, and in that direction only it will what read all the requests. So similarly, you just calculate the difference between all the different head movement and do the sum, and you will get the what total head movement and compare with the what normal scan, right? Another algorithm is what we call as a look, and the C look is the last one. So this is the version of the S scan. So arm only goes as far as the last request in each directions, then reverse direction immediately without first going all the way to the end of the disk. So understand, just go through the algorithms, right? So you will get the meaning of that words, what they are trying to say, right? So the C, so this is a version of the C S scan. So C look, so it will start from the 53. So the only thing is what, as you can see the algorithm flow, 53 to 65, 65 to 67, 98, 120 to 124, and then 183, but it's not going to touch the 199. So 183 to 199, that overhead is what miss out here. So again the better performance will be better, definitely the head movement will be less compared to the previous algorithm. And then from 183 it will move to the what very first tray, which is inside the request. So as you can see, the 14 is the what very first one, nearest to the 0. So it will go to the serve and that request, and after the 14 again it will not touch the what for, 0. So 183 to 0 and 0 to 14, that overhead is also missed. So 183 to 14 and then 14 to 37, that's it. Again just calculate the difference, and after the getting the difference and sum it, we'll get the what answer. So this is what all about the algorithm, how the algorithm works, right? So which algorithm perform better in what situations, which algorithm we will use. We can use the hybrid algorithm for the disk scheduling, the current computer system laptops, what type of algorithm they use. So understand the current laptops, they use what hard disk kind of technology, and that is quite different from the algorithms of the disk scheduling. So that's may not be applicable, right? So see, there are few things they had given for selection. So we know the throughput, we know the response, we know the how much time it will take to perform the IO operations, how much time it will take to head movement. So the difference, so that we have to be what calculate. So common head to natural appeal. So you can see, so it's better to combine the multiple algorithms and do the what executions accordingly. So we have to increase the utilizations, response time, IO, less waiting. So these are the common parameters, right? To perform the, and this will be help to evaluate the what and selecting criteria for the scheduling algorithm. So the second topic of this particular chapter, which is important, and nowadays we use that technology in networking, and when the systems are remotely located, and I have to be store the data into the multiple disk, not into the single one, because we are having a fear of to data get lost. So if you store data into the one disk, so it would be very difficult once data will get lost. So how you will recover the data? So there is a one technology come. So as you can see, the name of the technology RAID. So the meaning of that is what redundant array of independent disk. So data are redundant. Redundant in the sense, matlab the same informations are reside into the multiple disk. So data is redundant, right? For the we call as a replica. So same data will be stored into the multiple disk in a replication form. So the data is redundant, and that's array in the sense the 0 1 2 3. So we divided the every structure into the multiple structures, multiple disk structures, and it will be a sequence as an array, and all disks are independent disk, right? So there is no link between the disks. So disks are independently stored, And the independent again in the sense of suppose there are four systems situated in a network, so there are four different RAID, so all the RAID are independent, right? So we are having just link, the one data will be stored into the multiple RAID, and that RAID are linked with a network. So why? Because as a backup point of view, any failure case are occur, then we can restore, you can get the data. So that RAID technology is not available in our normal laptop in a system. So but in a big organizations, any company work, any corporate world, so they use it, right? Because they want to store the data into the multiple servers. So we can use the RAID to make the different server as well as, and it will provide the better performance and reliability, right? So let's see the diagram here. um, the multiple physical hard drives, and that's equal to the single logical hard drive. So understand means we are using what multiple RAIDs. So that will be the just for the understanding point of view, so how RAID is look like. So that's our disk only, right? Hard drives is how the hard drives work exactly. So we can have multiple hard drives added into our systems. We can have multiple slots, you can add multiple hard drives, so that will be work like that, right? So basically see the, the few things about it. So we need a reliable solutions where we can overcome the failure cases and my data will be stored safely. So that's a technology they have developed, right? And inside that you can see the disk will be stripping uses a group of disks as one storage unit. So the meaning is what the data will be divided into the blocks. So there are two types of information storing, we can say the bit wise and block wise. So that stripping is a type of the what block informations, right? Where the information is stored in what blocks. So the block size can be anything, right? So the another thing is what it's divided into the number of levels in the technology. So you can see the diagram over here, red levels. So basically there are seven levels, and the last one is level number 10. That's a hybrid one. So that's a hybrid level where we have to mix. So in this diagram you can see the red number, red level 0, we call it as a non-redundant stripping. So where the data will not be redundant, right? So that's different levels, right? So individually they started with level number 0, then level 1. So that's why the every level having some plus minus advantage and disadvantage. So that's why they are having multiple levels. So red level 0. So let me go to the next slide where I had explained. I'm going to explain you the individual levels. So see the red level 0 where we are dividing the data into the what strips, and each one having three size of the that particular level is what maximum 3. So 0, 1, 2, 3, 4, 5, 6, 7, and 9, 10, and there is no any replica. So that's why we call it a non-redundant stripping. So where the strip means the block of informations will be stored, the data is not be replicated. The next level is level number 1, we call as a mirrored disk. As you can see 1, 2, 3, 4, and the remaining 4 are the copies of the same. So similarly over here, so we are having 11, 12 strip of data, and similarly we are having 12 strip of similar data, we call as a mirror. So that redundant information. So in a red level 1 they implemented like that. So initially is red level 0, so where the actual data is get stored, but if suppose any data is lost for any of the failure cases, so my data will be lost. So that's why they want to keep that data as it is, so they make the what copy of the data that we call as a mirrored data. So the one backup will be available inside a red, so that is a red level 1. So advantage over the red level 0. So another level you can see the memory style error correcting codes, right? So the P stand for the parity bit. So I hope you guys are aware the parity bits, non-parity, parity, parity checking. So that's all are the encryption decryption mechanism, right? So parity means even parity might be maybe the odd parity with respect to one or zero, whatever, right? So you can see the red level 2, which is another version, so where we want to be ensure the informations will be transferred from the one red to another one, which will be accurate. So that is the what main motive. So when we are replicating the information from the one to another one, so we want to be assured there is no data will be get altered in between. So there will be no noise in the data, there will be no error into the data. So that's why we put the word parity. And parity is what bit wise, it's not byte wise, so it's bit information. So that's why in the red level 2 it's bit wise information, right? So that's the simple one. So you have to be calculate the parity bit. So as you can see the total 7 means 8 bit. So there's a 3 bit parity, so total 8 information, so I need 3 bits. So as you can understand, that's a Hamming distance. So that's another error checking mechanism, correcting mechanism, as you know. So we use the 3 bit, so 7 bit Hamming distance code. So 3 bit parity redundancy bit we use for correcting the information. So that is what the next level, where whenever we are going to put the information into the word as in copy to the next read level, so the I have to be make sure that informations will be stored correctly. There is no same information must be there, right? So I have to preserve that information. So that's another level of the red. As you can see the red level 3, so that is what you can see over here, bit interleaved parity. So I have stored the informations and individually I have a parity bit. So for the bit 1 2 3 4 the parity bit, another 5 6 7 8 another parity bit, another parity bit. So that's also work on the what a single parity bit information. So the informations which we are going to be stored and in a encrypted mode you can say, and we want to be assured that informations will be actual information. So that's a different method they are implementing to make it safe. Red level 4, which we call as a block interleave parity. So that's a block level. So 0 1 2 3 having a parity 0 to 3. That parity bit maybe the even or odd whatever, 1 and 0, even number of 1 maybe the odd number of 1, even number of 0 and odd number of 0, like that. So similarly block we convert, so now strip 4 5 6 7 having parity 4 to 7. Similarly strip 8 to 11 we are having parity 8 to 11. So that's another one. So in the as you can see, so the bit information converted to the strip one, and in the all the strip will having the parity, right? So that's another improvement in red level 4. So the implementation is different, else everything is what the similar one. We have to be keep data into the multiple uh, with multiple copies, so that will be redundant information. So in the red level 5, as you can see the structure of the informations. So there is a problem in red level 3 and red level 4. That is what we are using one disk structure to store all the parity information. So suppose that disk is get corrupted, then what? There are multiple levels of the disk and every having three layers, right? Maybe platters you assume. So if that particular block is lost, suppose parity block is get lost, so what then? How can I assure my information are actual one and correct one? So that's why they added another one, so the red level 5, where every level, every layers will having their own parity bit. So so means what, we distributed, so we distributed the parity block into the all levels of the block. So means the all informations will be there, and the individually that they are going to be what validate the information. So see that we call as a what block interleave distributed parity. So every block will be distributed and having the parity bit. So it would be easy. So in the last one, you can see the 6 and 10. So 10 is the advanced one. The 6 is having two types of redundancy bit, P and Q. So P and Q are the two types of, because the P for actual information, so the parity bit. For the parity bit, we need another Q redundant bit. So the multiple level where if suppose the redundant bits get corrupted, then how can I validate? So there another redundant bit they have added as a Q. So diagram is not here, so but you can understand with the red level fifth. So that's a similar one. In the last one, red number 10, it's a heterogeneous disk array. So where we are going to combine the 3 and 4, or maybe 4 and 5, maybe 5 and 6, and the combined red will be work as a red level 10, and that's we call as a heterogeneous disk array, right? So at the end, so let me summarize. So we are seeing the how the disk is structure, how disks exactly look like, the track sector, the size of the disk capacity, and then the algorithms we had seen. And you can do the same example with multiple exercise, so you would be clear about the how exactly it works, and how you calculate the total disk moment or seek time, maybe the seek distance. And the last one is the simple principle of the what RAID, the RAID technology. That's a very important one. You can explore the few more things about it by referring some good reference, and you can refer the our reference book, right, to get more about it. So thank you, students. So I hope you have to just revise it once, and it would be a workout. Thank you very much.